Any idea what the percentage of students is who are attending the first time? Because I can accordingly uh,
The
do a
percentage, but
recap.
yeah, the percentage of students who are attending for the first time would be, in my sense, around 30%.
Okay, I'll just try to. Obviously, I can't repeat what I did in the first two classes, but at least set the context for the question we are dealing today by recapping whatever the bare minimum required to understand today's session.
Yeah, and one more thing, Omkar, what I'm also observing is that sometimes when timings do not match for the students, obviously it's best when they attend it live,
Hmm.
but when timing is not matching with the views I'm seeing on YouTube channel, it seems a lot of people watch it later.
Okay, that's fine.
Yeah.
Yeah. All right. This is our third session together, and we are going to uh, continue from where we left off last time. So, just at a high level, um, we were imagining asking this big question of, what our place in the universe is. That was our launching point for a study of physics. Can we come up with a map or a 3D model of the universe based on what we see around us? And um, so what I'll do is I'll just recap what the main question was. Specifically, today we are going to look at, as the title of the session says, we are going to focus more on the Earth than the whole universe. But as you'll see, we'll end up looking at a physics that was thought to apply everywhere, and we are going to then recap what the arguments were for a flat Earth and look at a few variations of that. And I'll go through this quickly. The bulk of the session is going to be on a transition from a flat Earth cosmology to a spherical Earth cosmology, and that it is during that transition that we will develop a new physics that will be much better than the rudimentary ideas we had last time.
Omkar, just one moment.
Hmm.
I quickly want to give another perspective because I am more of a layman and you are more of an expert. I think, guys, the way we are trying to approach this whole thing is, first of all, we are trying to understand physics from a perspective where physics is not just about being able to solve questions by applying some formulas and understanding what those formulas are. Do you understand this thing? Let me repeat what I'm saying. And Omkar, give me 2, 3 minutes. Let me just set the context with respect to a layman because I'm fascinated by what you're trying to do. So, first of all, the first thing that we are trying to achieve is your coaching, your school is tied by the requirement which the external environment has from them, which is हमारे बच्चे को पढ़ाओ उसको जेई या नीट क्लियर करना है बाकी किसी चीज में टाइम वेस्ट मत करना सो द फर्स्ट थिंग इज ऑल ऑफ दोस external support systems, be it coaching, be it school, they're trying to teach you in terms of F is equal to MA, V is equal to U plus AT, S is equal to UT plus half AT square, or conservation of momentum or conservation of energy, whatever, right? We have not reached those things at all till now. We are in the third class, right? Is this clear to everyone? This is very, very important to understand. What we are trying to do here is we are trying to understand how our forefathers, how people from time immemorial have tried to understand what is happening around them in nature. And when they were not able to understand, all kind of laws started getting developed, all kind of postulates, all kind of hypotheses came in. One of those hypotheses was the flat earth hypothesis. The way we are trying to understand physics is how our forefathers have tried to understand what is happening in nature. They came up with ideas, they tried to test those ideas, and over a period of time, some of the ideas started explaining things in a more holistic fashion rather than explaining just specific use cases. So we studied flat earth hypothesis in the first class. Now we are going to study Socrates. I'm saying Socrates, I'm sorry. Aristotle's spherical earth hypothesis. And hopefully in the next class, we are going to move to what Galileo was talking about, and at some point of time, we are going to come into Newtonian mechanics.
All right, so imagine, again, I'm just recapping the problem. Imagine living 3,000 years ago in a world where, there were no computers, no mobile phones, no electricity, no modern science, and none of the technological products of no modern science. There are no planes flying around the world. There are no ships sailing around the world. And uh, you are living in a farming society, maybe in India, maybe in Greece. Um, and so your beliefs about the world would have been very different. And so the question that we are trying to focus on is, if you were living, let's say, 3,000 years ago, what would you have believed the universe to be like? Specifically, what would you have believed the shape of the earth to be? So, till now, we have looked at uh, a rudimentary flat earth cosmology, but let's just um, focus on the shape of the earth for today, and you'll see that it connects to the broader cosmology as well. So, what would you believe, and what reasons would you have offered in support of that belief? So, that's the question. Now, would it have been important or relevant at that time? Of course, because the way we look at our place in the universe governs, how we think about ourselves, about who we are, and what is the goal of my life, what is my place in the grand scheme of things. Is it relevant today? Well, today we kind of know what the shape of the earth is, but trying to understand how humans figured out the shape of the earth is an exercise in understanding what really is the nature of science. What does science in its earliest, most elementary form look like? So, in that sense, it's relevant. Right, so today's answer is that the shape of the Earth is an oblate spheroid. It's not perfectly spherical. It's a little bit flattened on the poles, a little more bulging out near the equator, but as such, it is approximately a sphere. But when thinking about this question, we should not be uh, making use of satellite pictures which show from different angles that the Earth is a sphere. So just subtract all that knowledge out from your brain. Your teachers might have told you that the Earth is spherical. Subtract that knowledge out also, because we are asking how do our teachers know what the shape of the Earth is, right? So if you were living 3,000 years ago, you would have to figure out the answers from scratch. You could have tried to figure out the answer by walking in a straight line and seeing, where you end up. But the problem is, sooner or later, your path would be blocked by tall mountain ranges, thick forests, vast open oceans, cold, snowy areas. And so, if you were living, let's say, in Greece around that time, the maximum you could do is to maybe travel around the Mediterranean, across the Mediterranean, and to Western Europe. You can see that the Greeks had actually colonies all around the Mediterranean because they were seafarers. And you might hear travelers' tales, but basically, this is roughly the region of the earth that you would have information about. And so, just based on that, how could you figure out the shape of the earth? We have seen earlier that when we say that the earth was, we probably would have thought the earth is flat. We are aware that there are mountains and valleys, um, and so the surface of the earth is not literally flat. But when we say that the earth is flat, what we mean is, if we were to, uh, rise up higher up in the sky and look at the broad shape of the earth, then we would see that on the whole it's flat, right? Like the surface of a table, even though as you zoom in, you see those mountains and valleys. But at the highest level, it would be flat, something like this. Although what we had last time was the edges of the earth reach all the way to the edge of the universe, right? Because the flat earth was at the center of a spherical universe, as you might recall. So you can imagine that picture instead of this. So like I said, the surface of a table is uneven, but we still call it flat. And so even though the surface of the earth is uneven, we might choose to still call it flat. But what arguments would we offer in defense of a flat earth? And we looked at a couple of arguments actually last time or in the first session. The first argument was just based on common observation that if you place yourself in the middle of a grassland with no mountains, no fog or dust blocking your view, and if you look around, you'll see the land is flat no matter how far your vision goes. You could do the same thing if you were in the middle of the ocean. You would see the water extending away, forming a flat surface. So even though the surface of the earth does become uneven where there are mountains and valleys, on the whole, the overall shape, based on observations, would be flat. And so mountains and valleys, I told you, would be treated like the minor creases produced by the folding up of a towel on a flat surface. So a second argument that I had mentioned was that if you observe the sun rising or setting on the horizon, and if you look at it at a point where it's partially above the horizon and partially below it, you'll find that the horizon cuts across the sun in a straight line segment. And this is what you would expect to see if you were standing on a flat earth. If you are standing on a spherical earth, then this section of the horizon or even the broader horizon would appear to be curved like that and not a straight line segment. Like for example, if you take a tennis ball with a Lego figure on top of it and you imagine yourself as being in the shoes of that Lego figure, what you would see as the horizon or the boundary between the earth and the sky would be that the section of the ball that cuts across the sun would be curved. Right? So hopefully that makes sense. So this means that the earth must be flat, the fact that this horizon is straight and not curved or spherical like a tennis ball. Okay, so that's the second argument. Now, a third argument, which is something I didn't mention, and this argument came up because there were people who started claiming that the earth is spherical. And just to show you how absurd it looked to people of that time, uh, common experience shows that any solid or liquid object falls down when left in the air. And that's why it's impossible to stand upside down from, say, the ceiling. But if the earth is spherical, then you must be standing on the top hemisphere of that sphere. If you were standing anywhere on the bottom hemispherical surface or even on a, steeply sloping surface on the top hemisphere, you would have fallen off the earth. So it's absurd to think that there are people walking on the bottom hemisphere with their, feet above their heads, living on land where the trees are growing upside down. Um, and so this argument, I'll just give you a quote from an early Christian philosopher um, called Lactantius, and in one of his books called The Divine Institutes, he says, "Is there anyone so senseless as to believe that there are men whose footsteps are higher than their heads, or that the things um, that the crops and trees are growing downward, that the rain and snow and hail is falling upward to the earth?" Lactantius here is referring to people living on allegedly on the other side of the earth with their feet up, and those people were in those days known as antipodes. These were hypothetical people who are living on the other side of their earth with their feet pointing against you. So that's where this word antipode comes from. Pod for, the foot, like podiatrist is someone who cares for your foot. So an antipode would be someone who has their feet pointing at you on the other side of the earth. So this was the very notion of a spherical earth was viewed as an absurdity, even after, many people had started believing in it. And this was the argument. Now, this argument actually assumes a notion of space that, I talked about last time, which is that space in our spherical universe is thought to have um, direction. So if this is our flat Earth, we say that this direction was up, this direction is down. And so if we were to replace the flat Earth with a spherical Earth, right, floating in space, then the argument is that people living on this side would actually fall down, right? In fact, the Earth itself, the entire Earth itself should fall down. And we saw that there were a few different variations. Let me just briefly recap them. Um, one
Sir,
of the one of the uh,
sir,
yeah,
I, there is one more argument that comes to my mind in like for the flat Earth. May I?
sure.
Um, so because we're humans, I also think that we're limited by like we're also afraid. We were and still are also afraid of the unknown. So even if people could create ships, to cross waters and they could climb mountains and everything. They still did not because the fear of leaving the known territory was kind of scary. So I think for a long time, that could also be one of the reasons why people thought the Earth was flat because they never explored.
Yeah, but they were also limited to the extent they could explore. For example, there were no ships that could that were the technology, sailing technology was not so powerful at that time that you could have ships that could literally circumnavigate, the world, even if they wanted to. So there were obviously a few bold adventurers in every era who tried to explore as much as they could, but it
It
would
was
still
yet
have been
again
very,
limited.
very limited. Like, for example, you couldn't cross the Atlantic Ocean, which is
Yeah, yes.
right, so, or the Pacific Ocean. So that would be a big constraint.
Yeah,
Uh,
yes, yes, sir.
so I mentioned, this particular popular flat Earth viewpoint, which is that you have this circular disk um, of making up the Earth, the landmass of the Earth, and this is floating on water. So this view is attributed to the earliest of the philosophers in the Western tradition, called whose name was Thales. Uh, he was the very first Western philosopher. He was a mathematician, an astronomer. If you've done geometry, you might have studied Thales's theorem that, when you have an angle in a semicircle, that's always a right angle. Um, and he was known as one of the seven wise men of ancient Greece. And being a philosopher, he, tried to argue whatever he believed. And so it is often said that he is the one who came up with the notion of a proof in mathematics as well. And, Thales's theorem and some of the other claims he made in geometry could be easily proven from self-evident axioms. But here we are talking about his view on the shape of the earth. And Aristotle, who um, lived later, uh, is the only source for us about what Thales said on this matter, because Thales' own writings did not survive. So the oldest theory for um, the shape of the earth is that the flat earth rests on water, and it's attributed to Thales of Miletus. It was supposed to stay still because it floated like wood and other similar substances. Okay. So that's the view that Aristotle is quoting. There were obviously older views, but he's referring to the oldest philosophical views. Remember, a philosopher is someone who not just uh, deals with big questions, but who takes the responsibility to justify whatever they, believe are the answers to those questions. So that's what Thales did. Now, another variation of this flat Earth viewpoint, which is actually quite significant, was given by a philosopher named Anaximander, who lived almost at the same time as Thales and actually in the same city of Miletus in Western Turkey, what is today Western Turkey. Anaximander actually seems to have noted the fact that if you look at the horizon, you have the stars, you have the pole star and you have other stars that are, rising and setting in all directions. And it would to him, it felt odd that these stars are plunging into the ocean, right? That he wasn't really happy with that particular view. So what he felt is that the trajectories of the stars should continue unimpeded rather than being blocked by the ocean, and somehow inexplicably, they are not stopped by the ocean, but uh, that model did not appeal to him. So he felt that there should actually be empty space underneath the earth into which the stars descend. And so he came up with a flat earth view, in which the earth was flat at the top, but on the whole cylindrical in shape. But that's not the main point. The main point was this cylinder is actually floating in empty space. So his view of the universe, therefore, was that inside this spherical universe, you have this cylinder that is cylindrical Earth that is at the center, and it's just floating there in space. Now, why wouldn't it fall down? Remember, if space has this orientation, then a solid object, like in fact the entire landmass of the Earth, should actually fall down. So why doesn't it fall down? Once again, Aristotle tells us his argument. Uh, Essentially, the argument is that we should we should not think of space in this way. So Anaximander actually changes our notion of space. He said that in a perfectly spherical universe, space should be treated as in a different way. Anything that's away from the center is what we should define as up. So that's up. Anything in that direction. And anything that's directed towards the center of this spherical universe, that's what we should call as down. And so if something is um, dropped from the surface of the earth, it tends to fall down. Well, it's actually trying to fall down, as in towards the center of the universe. But if the earth is already at the center of the universe, then there is no further down, right, for it to go, or to descend into, because it is at the deepest possible place, which is the center of the universe. So this is just a quote from Aristotle's work, where he says that Anaximander claimed that the earth keeps its place at the center of the universe because of its indifference. Now, this is just a word which means, there is no particular direction in which the earth should move, because all directions are equally feasible, right? There is no reason to give priority to one direction over another in a spherical universe. So motion upward or downward or sideways are all equally inappropriate, right? To something that is at the center of a perfect sphere. And so if you say that, well, the earth should fall down, then somebody could say that, well, the earth should go in that direction. And it's contradictory to say that, these two directions are contradictory. And so you know, uh, and so the argument goes that the earth therefore cannot move in any direction, because all directions are equally um, feasible or infeasible. So it just remains still. But this is the way you can understand it, that Anaximander essentially changed our view of space, to say that anything going away from the center is what we should call as up, and anything towards the center is what we should call as down. And this is a reorientation that we are actually going to see is going to be preserved for the next 2000 years. There were other variations. I won't go into the details, but there's one philosopher who claimed that uh, the flat circular Earth is actually resting on air, right? And the reason it doesn't fall down is that the air doesn't have room to actually flow out from under the Earth, just because it extends all the way till the Earth extends all the way till the edge. So you don't need water under the Earth; even air would do. And the reasoning here might have come from looking at tornadoes that seem to be able to carry heavy objects, and whirl them around. And so he thought that air actually is a more reasonable candidate than water, that which Thales had. Xenophanes, I mentioned actually the view that he had, which is that the Earth literally extends down forever. It's infinitely extending down, and so uh, it cannot fall because it's extending down forever. And so there were all these variations. You couldn't argue in favor of or against any of them because these were all speculations, right? Good speculations, but they were still speculations. You couldn't use evidence to uh, prove or disprove any of these views. And there were many other views, uh, many other variations of a flat Earth view. But anyway, so let's come now to how things changed. How did people decide that this flat Earth cosmology is not the right cosmology to work with? We should, you know, change our views. So we don't actually know who first came up with the idea that the shape of the Earth is actually spherical and not flat. There are contradictory, uh, claims on this matter. Like some people claim that Pythagoras was the one who first claimed the Earth is spherical. Others attribute it to, other philosophers. So we don't exactly know. But what we do know is that the earliest surviving text, which references a spherical Earth, is a text by the Greek philosopher Plato, um, who was actually a student of Socrates. So um, Plato, in one of his dialogues, so Plato's writings are in the form of dialogues, generally between his teacher Socrates and other people who Socrates debated with in Athens. And so, in one of his dialogues, Socrates, the character Socrates, says that my conviction is that the earth is a round body in the center of the heavens and therefore has no need of air or any similar force to be a support. So, he seems to kind of accept Anaximander's view that if you're already at the center, you don't need any support because that is the furthest you can descend. So um, s- you know uh, s- this dialogue, Phaedo, is actually the dialogue that records the death of Socrates, who was executed by poisoning by the people of Athens, and you might have learned about that in your history. And in this dialogue, it is Socrates himself who's making this statement, declaring that he's convinced the earth is spherical shortly before he died, or shortly before he was poisoned. Now, Aristotle was a student of Plato. So Socrates had Plato as one of his students, and Plato had Aristotle as one of his students. And so it's not surprising that Aristotle believed that the earth is spherical. But the important thing is Aristotle gives arguments for why or how do we know that the earth is spherical. And it is from this work that uh, we are going to get our earliest arguments in defense of a spherical earth. And so we're going to look at them now. So once again, our framework is that we have a spherical Earth, we have a flat Earth at the center. That's up. All these directions are up. And um, these directions are what we would define as down. Okay, so keeping this notion of space in mind, um, Aristotle is going to argue that this particular view of the shape of the Earth actually makes the most sense. And the way he did that is by um, uh, building a physics which predicts, which explains why the Earth must be spherical. So it gives a mechanism for how or why the Earth must be spherical. So before um, uh, s- uh, before we look at other observations based on sense experience, I'm going to give you an overview of what Aristotle's physics is. So, according to Aristotle, if you look at objects around you in your daily life, they are of they are essentially made of four different elements. So today we have, the periodic table in chemistry, which, you know, where I think you have 92 or something naturally occurring elements. But for Aristotle, all matter is made up of essentially four elements. And he called those elements as earth, water, air, and fire. Today we can rename them as solid, liquid, gas, and heat. So for a long time, actually till just a couple of hundred years ago, people used to think of heat actually as a substance uh, rather than a way to transfer energy. So it was literally thought of as a substance. So solids, liquids, gases, and fire or heat. So what is what is the property of a solid? The main property for Aristotle was that if you take a solid object and you drop it, its natural tendency is to fall down, that is, to move towards the center of the universe. In fact, the same thing is the property of water as well. It also tends to move towards the center of the universe. But if you have a mixture of solid and liquid, the solid has a greater tendency to move towards the center of the universe, which is why you find solids sinking in water. For example, if you look into the ocean, you see that the landmass of the Earth lies under the water. So the rocks, for example, have a greater proportion of earth in them, and so they sink in water. Whereas if you take wood, for example, the reason why wood floats on top of water is because it's not pure earth. It is actually a mixture of earth with a lot of air inside. And air is a third element, uh, which actually has a property that is the opposite of um, earth and water. It tends to ascend away from the center of the universe, which is why if you have bubbles inside water, the bubbles tend to rise up, as you might have observed, away from the center of the universe, unless something blocks the bubble. Okay, if your path is blocked, then of course you can stop there, but otherwise air would just tend to rise up. And fire is actually the lightest element. So for Aristotle, earth and water were what he called as heavy elements or gravitas, right? He said that they have gravity, but for him, what gravity meant is simply the fact that they are heavy, and so they tend to fall towards the center of the universe. Whereas air and fire are light elements, which means they have an active tendency to ascend away from the center of the universe. And fire is lighter than air, which is why when you light a fire, you see that the flames rise up through air. And so these are very commonsensical properties that we observe with our eyes. And you can use this to explain a lot of things. For example, if you heat a pot of water on a stove, you're adding fire to it, right? So the element fire enters water and it makes the water lighter, which is why hot water tends to rise up. Uh, and in fact, if you keep boiling water, then there is so much of fire added to it that it becomes steam and then it rises up, right? So um, that's how clouds can also form when there is, some of the water is mixed up with a lot of fire. Uh, Clouds are formed because the water rises up. But then um, when the clouds give off some of that fire, then they become heavier. And so the water in them then falls back as rain. So it's a very commonsensical physics, but a very qualitative physics, and you can use it to explain a lot of things. But natural motion of anything on Earth, according to Aristotle, is always linear, and it's either towards the center of the universe. If unblocked, we would call that as free fall motion, right? Falling down. And for air and fire, it's actually rising up, right? Or away from the center of the universe. Our own bodies are made up of a combination of earth, water, air, and fire. So in general, every object that you see around you is a combination of earth, water, air, and fire in different proportions. So um, our own body is a combination of that. So, for example, the reason why our body temperature is warm is because there is fire inside us. Of course, air we know is inside us. We breathe in air. Water, there's a lot of water in the blood. And of course, we have solid body parts as well. Now, just based on this common observation, uh, this is not the entirety of his physics, but uh, uh, this is what we need to focus on for now. These are the four terrestrial elements. That means the elements that make up what we call as the Earth. By the way, the landmass we live on is called the Earth because most of it is dominated by the element Earth. Um, and so this Earth doesn't refer to the planet, it's referring to that element. And the fact that we call our planet as Earth is because most of it is solid. So if you accept this, then it must follow, according to Aristotle, that the Earth is spherical. And here's his reasoning. So suppose you have a spherical universe, and we don't know what the shape of the Earth is wherever it is. Just imagine in your mind blasting apart the entire landmass of the Earth and hurling every piece of it in all different directions in the universe. What will happen? What will happen is that the pieces or the particles of Earth are going to tend to fall towards the center of the universe. Okay, so they will tend to fall towards the center of the universe and they will actually accumulate, aggregate together at the center of the universe. Next, water. Water, the particles of water will also fall towards the center. They will aggregate, but they will aggregate around the solid Earth, right? Um, so the thing is, our so-called planet Earth, remember, it's a misnomer to call the Earth as a planet because it's really stationary. Uh, but the landmass we live in is at the center of the universe because that is where the elements earth and water will naturally gravitate to. So where else could it be except at the center? Now, why is the earth or why must the earth be spherical? Well, imagine all of these different particles jostling and pushing each other to come as close to the center of the universe as they can, right? What is the best possible arrangement that can satisfy the maximum number of such particles so that they are as close to the center of the Earth as possible? Well, that arrangement would be a spherical arrangement because if you had any other arrangement, if you, for example, had a flat Earth, then if you had a flat Earth at the center, that's not really uh, a good or a plausible shape because when you look at these particles of Earth are pretty far out from the center. And so if they were to rearrange, um, they could get closer. And so the best possible arrangement which will satisfy most of those particles would be one where the Earth is spherical and at the center. Okay. Now, the reason why there are mountains and valleys, according to Aristotle, is because, we haven't yet given enough time for things to, perfectly become spherical. Uh, and it also follows that the Earth must be stationary because uh, once you're already at the center, there is no further tendency to move. And so, from this simple physics, it must follow that the Earth is at the center of the universe, it is stationary, and it must be spherical. Okay, this just follows from his physics. And here's a quote from his work. Its shape must necessarily be spherical because every portion of the Earth has weight, uh, you would say gravity, uh, heaviness, until it reaches the center. And the jostling of these different particles, some bigger in size, some smaller in size, that would not produce a surface that has, big ripples in it, but rather like Play-Doh. If you've played with Play-Doh as a kid, you just push it from all directions. That's how actually you make a spherical, shape it into a sphere by compressing different parts from all sides, you get a spherical shape. Now, this sounds well and good, except that when you look at the night sky, you see circular motion. For Aristotle, there is no reason for circular motion to happen because things either fall down towards the center of the universe or they go up, right? So firstly, how would Aristotle explain why some things move horizontally, right? For example, if I take a ball and I throw it, uh, as soon as it leaves my hand, why doesn't it fall down? Why does it keep going in that parabolic
So,
trajectory or whatever you say? Uh, According to him, uh, motion
so
is of two kinds. One is natural, which is what I've talked about, but there's another kind of motion which he called as violent. You can think of it as unnatural. It is unnatural because it won't happen on its own unless and until a soul, right, a living thing, initiates it. So the property of a living thing is that it can initiate motion because of the, presence of, uh, some kind of soul. So violent motion is what the motion of a ball is. So suppose I take my hand and I throw the ball. The reason it's moving horizontally is it's because it's being pushed by my hand. Now you may ask, well, after it leaves my hand, it still continues to go, uh, uh, let's say in that direction, right? Maybe that's how it falls. So why does it keep going in that direction? Well, according to Aristotle, the reason why that happens is that there are, air, particles of air here, right, in front. And as the ball tries to go ahead, these air particles are pushed around it. So they come around it and they push the ball from behind, making it continue going forward. Because what would happen if these air molecules did not come around and push the ball from behind? This ball would go forward and there would be vacuum here. There would literally be vacuum there. So for Aristotle, there is no such thing as vacuum, right? So um,
so why?
for the ball to move forward, air must come and fill that space, and as it fills that space, it will hit the ball and cause it to move forward. But this effect weakens over time, which is why the ball eventually ends up falling down. Yeah, somebody had a question?
So for why did the concept of vacuum did not exist for Aristotle?
Because everything in the universe for him was made up of these four elements. Actually, I haven't talked about the fifth element yet, but everything was made up of these four elements. And so uh, uh, empty space, I guess, for him would also not serve any purpose, right? So Aristotle had this view that everything in the universe has a purpose and a natural purpose towards which things move. And uh, so for him there was actually no such thing as a vacuum, because I mean, even if there was vacuum temporarily created, um, you would have something fill up that space, right?
Okay,
So
so
it,
in
it
this
wouldn't
case,
wouldn't last forever. Yeah.
it would be air, like his thought process.
Yeah, in his thought process, as the ball is moving forward, see, the ball is entering the space that's occupied by this mass of air, right? So that mass of air needs to end up occupying the space that the ball was occupying. So how will that happen? Well, it moves
Right,
around the
right.
ball. It moves around the ball and ends up occupying this space. So at the next time instant, when the ball is here, uh,
Uh,
the air that was here would have moved there, and as it moved there, it would further push the ball, right? Maybe not with the same force that our hand had thrown it with, but enough force that it keeps going forward, at least, you know, in a weakened sense, right? So this keeps weakening until because then that's why you see the trajectory of the ball becoming more and more vertical uh, because vertical motion is natural.
Yes.
Horizontal motion is not, it's unnatural. He called it as violent, but it can happen, it can continue for some time because of this kind of mechanism.
Right, I understand. Also, sir, there was one thing that I wanted to mention. Before Aristotle, like from what I read, before Aristotle began to study about, about motion, and as he began to develop theories about why Earth is spherical, there was one observation that he made, and that was when ships sail, they, eventually we could not see them. So, like, what he came to the conclusion was that they were like going down. And so, you know, the water is a flat surface, so it cannot literally go
Yeah.
down. So figuratively, the earth had to curve somewhere because we could not see them after a certain point.
Yeah. So that argument actually is a later argument. It is first found 300 years after Aristotle. So Aristotle didn't give that argument. It was given by Ptolemy. I actually have that later on in this presentation. So I'll
Oh,
go
okay.
over all of Aristotle's arguments, and then I'll add a couple of extra arguments that people came up with later, and one of them is what you're referring to.
Oh, okay. I'm sorry. I thought
Yeah.
Aristotle said. I'm sorry.
No, and actually, it's an interesting, and for me, it's like an open question. I've asked a number of professors here from Harvard and Brown. I had communication with them on this matter as to why that argument is not found earlier. How is it that Aristotle didn't give that argument? But I don't want to, you know, jump further ahead because I'm going to talk about that later. But
Yes,
this
of course.
argument is a philosophical argument, right? He's coming up with a physics. It's the prop he's relying a lot on reasoning, right?
Yeah, yes.
What follows from his physics? From his physics, it must follow that the Earth is spherical. And he's
Yes,
explaining the
yes.
mechanism. The mechanism for how it becomes spherical is you have earth and water, the heavy elements, trying to move towards the center of the universe, and the lighter elements trying to move away. And so you have uh, you know that's why you find on the earth that natural motion is always vertical. Even when a ball comes down an inclined plane, it's coming down, right? It can't fall
Yes,
vertically through the inclined plane, but by coming down, it's actually getting closer to the center of the earth, which is really the center of the universe. So that's why it rolls down. um,
right.
and so that's, unless it's blocked, it will, things will tend to fall down. And anything that appears
Eventually.
to violate that vertical motion is because somebody is initiating this violent or unnatural motion, which is which can continue for some time, but it cannot continue forever. Like you might throw a ball horizontally, it will roll on the surface for some time because of this mechanism that I mentioned, but eventually it will come to a halt.
Yes, sir.
So that is what he said. Now, there is something in our observation that contradicts this kind of free fall motion that he predicts for Earth and water. And that is, if you look at the night sky, we have already seen how the stars appear to go in circles, not just the stars, but the planets, the moon, the sun, they all appear to go in circles um, around some center where the pole star almost is, right? So how do you explain circular motion? Well, Aristotle's natural reasoning was that the substance that the planet, stars, and the sun and the moon are made of must be something different from the four elements that we see on Earth. And so he postulated that there is actually a fifth element, which he called as quintessence, the fifth element, but other philosophers later called it as ether, which is found in the celestial realm, not on the terrestrial realm where we don't see circular motion happening forever. Uh, but in the celestial realm, everything is made of ether. And the natural tendency of ether is to move in circles. So just make that a fundamental property of that fifth element, and you don't need to explain why things are going around in circles. That's just their nature. And philosophically, it also makes sense because a circle has no beginning and end, right? So it's kind of representing eternity. There's no start, there's no end. And so in the celestial realm, it makes sense that this perfect element, ether, tends to go in circles, signifying uh, that it's an eternal realm, right? Things are not born there, nothing gets created there, and nothing gets destroyed in that realm. Whereas on the terrestrial realm, things are born, they are imperfect, they die, there is change happening. But in the celestial realm, things just are the way they are forever, right? And so ether is the substance that the sun, the moon, planets, and the stars are made up of, which is how their circular motion is explained by Aristotle. So the physics of Aristotle uh, is actually uh, separating the terrestrial realm from the celestial realm, because the celestial realm is made up of a completely different substance with completely different properties. And so we can say that physics itself gets divided into two, one that applies to the terrestrial realm and another physics that applies to the celestial realm. And both of those, you can say, are part of the same physics, but there's no overlap between these two realms, right? There's no realm where you find ether mixed with earth, water, fire, and air. It's like a perfect separation. And what you see on the right side is like a diagram that represents uh, the structure of the universe. So it's a series of concentric shells, right? 3D shells. Even though this is a 2D diagram, these are not just circles, they are representing 3D shells. And at the very center, you have the solid earth, right? Made up of earth and water, the elements earth and water. And then around it is the atmosphere, or as we call it, the region where you have air and fire. And then beyond it, we have the realm of the moon, right? So up to this point, everything inside this shell is the terrestrial realm. And once you cross it, you are in the celestial realm. So the moon, the sun, and the other five planets I talked about, um, and at the outermost edge, the starry sphere, the celestial sphere, they are all part of the celestial realm made of ether. Uh, and the reason why planets, the sun, the moon, and why the planets, the seven planets appear to move separately from the stars, right? They are not perfectly in sync with the stars, is because um, they have their own shell, their own inner shell, which rotates with a different angular speed from the outermost starry sphere. And that's why you see relative motion happening between the planets. That's why the planets wander independently of each other too. So each of them gets its own sphere in Aristotle's cosmology. And so this is the broad cosmology that was, um, you know, accepted for more than 2000 years. There were details added to it, there were adjustments made, but at a high level, it remained persistent. And this was the cosmology that Copernicus, Galileo, Kepler, Newton, they were trying to replace with a new cosmology. Now, here's the thing. There is a reason why you have this cosmology with the Earth at the center, right? It follows from Aristotle's physics. So you can't just change the cosmology without giving a new physics that explains um, how the sun, for example, could be at the center, which doesn't make sense from Aristotle's physics perspective, right? You have the sun at the center, something made of ether at the center of the universe, and then you have something made of earth and water going around it in circles. That's not the natural property of earth and water. So it's just absurd. That kind of model is just absurd. It doesn't uh, fit with his physics. And so unless like you have a new physics uh, to support any new astronomy you come up with, nobody's going to take it seriously. And for good reason, right? Because we don't just want the kinematics of how things move, but we also want to understand the dynamics. Why do they move the way they move? And so Aristotle's physics has both, right? He explains the kinematics uh, with uh, with the dynamics, right? Of course, his dynamics is pretty qualitative, as I mentioned here. It's not quantitative, but it was very commonsensical. And in fact, when you start studying science, when you start studying Newtonian physics, one of the challenges you will face is that our common sense actually is completely in alignment with Aristotle's physics, which is why we have conceptual difficulty in understanding Newtonian physics because it actually goes very much against our common sense. Um, so I hope you can see here that Aristotle's physics is very commonsensical and logical. Now, this was actually his main argument for why the Earth is spherical, his physics. From his perspective, this the spherical shape of the Earth is established. Nothing more needs to be said. But being a philosopher, he said, I'm going to give you more evidence from the senses. And this doesn't explain why the Earth is spherical. These additional pieces of evidence are just justifying how do we know that the Earth is spherical? How can we verify that the Earth is actually spherical from our sense experience? And so, another powerful argument he gives uh, comes from our understanding of eclipses. And I do need to explain uh, how the ancients thought of eclipses and how philosophers in particular came up with an explanation for how lunar and solar eclipses happen, which are still found in our science textbooks. It's a it's an amazing piece of reasoning which was correct thousands of years ago. This was actually going back even before Aristotle. In fact, the person who came up with the right explanation of eclipses himself believed the Earth is flat. And he's the one who actually gave that argument by looking at the sunset for why the Earth is flat. That same philosopher, Anaxagoras, is credited with coming up with the explanation for eclipses. So, what is an eclipse? Um, Ancient people were very well aware of it. In fact, it was a frightening event for them. It's an event which seems to violate the natural order of things because uh, they are very rare, right? So, sometimes you have the astronomical bodies like the sun and the moon becoming temporarily obscured. Like in a lunar eclipse, the moon is obscured. In a solar eclipse, total solar eclipse, the entire sun is obscured. And so, how do we explain this? Well, in different cultures, including in India and China and pretty much everywhere around the world, eclipses were um, not considered an auspicious event. So, um, this is actually a statue from a temple, a Buddhist temple in, I think, in Thailand, where you see this demon Rahu, who's also found in, Hinduism, Buddhism, Jainism, common. Um, he is swallowing the sun, right? So something was thought to be attacking the sun and the moon to cause an eclipse. And so there were different, of course, stories behind, why is it that this demon exists? He's invisible for most, he's invisible except during the time of an eclipse when you see him uh, based on the effect of his swallowing or attacking the sun and the moon. And so some kind of demon, some kind of creature that was attacking the sun and the moon was the common cultural explanation for eclipses everywhere around the world. So how did that change? Well, I'll tell you the
So there's
steps.
something that I don't understand,
Okay.
and this has been like a doubt for a while. I do not understand why, like, we cannot completely, like, when people cannot explain something completely by, with logical arguments and, you know, fact-based arguments, they just kind of bring some supernatural element into the explanation. Like it has always happened.
Yeah, so the
So, like,
distinction between natural and supernatural was not there in ancient times, right? Because there were a lot of things that you just couldn't explain unless you brought in what we would today call as supernatural, but that distinction itself was not there. So there had to be some story, right? Typically why something exists was explained using stories, and stories were the primary way in which cultural knowledge was passed on. So you can say, well, some of the stories were correct, some of them were not something that we would consider today as correct, but people learn in the form of stories, and that is actually the reason why we find these modern subjects hard to understand, because our brains have evolved to learn primarily through stories. And so can't really blame them for relying on stories to uh, for explanations behind important events, something as important as an eclipse. Entire battles would stop when eclipses happened, because the two warring armies uh,
Yes.
would think that the gods are not in favor of what's happening, and so they would uh, um,
So,
um, yeah. So how did things change? This is actually the point where we can say that science is beginning. Okay, what I'm about to describe are, you can say, the first baby steps that were taken by philosophers, which we can distinctly identify as scientific steps in the ancient world. So let's look at the moon. Everyone knew that the moon goes through phases. We know that's how a month is defined. And so why does the moon go through phases? And again, different cultures relied on stories, where the moon god does something bad, and because of that, light, he's given a curse where some of the light, he loses his light, right, every now and then, and until he takes a bath in the ocean, he's condemned to um, not be luminous, but over time he regains his light only to lose it again, right? So the curse is only partially revoked and not fully revoked, which is why he keeps uh, losing his luminosity every month. So, but the point is that the ancients thought of the moon as having its own light. Just like the sun has its own light, the moon was also thought of as having its own light. And so the phases of the moon were explained again using, stories. But one of the early philosophers, whose name was Parmenides, he made the following observation of patterns that you see in the night sky. One of the patterns that he saw is that when you have a crescent moon, a thin crescent moon, it always seems to be facing the sun, right? For some reason, it always seems to be facing the sun, no matter where it is in the sky. It's always pointing at the sun. So why should that be the case if the moon's light is intrinsic to it? Why should it always face the sun? Another hypothesis, another possible hypothesis is that, well, the moon's light is not intrinsic to it. Maybe it is reflected light from the sun. So, so now you have two hypotheses, right? Either the moon's light is intrinsic to it, or it's borrowed from the sun. So how do you distinguish between these two hypotheses? Well, the second hypothesis makes the prediction, or it leads to it necessitates that a crescent moon, in fact, whenever you see light on the moon, that part of the moon is always facing the sun. Whereas the first hypothesis, which says that the moon's light is intrinsic to it, that does not have a proper explanation for why it should always face the sun if the light that it has is always intrinsic to it. Right? So the second hypothesis seems more convincing, because of which Parmenides seems to have given it. And again, we don't have any writings left by him, but there is just a fragment that's quoted by someone else, that the moon is a body shining by night, wandering around the earth with borrowed light. So this phrase, borrowed light, ever peeking towards the rays of the sun. So this view is called heliophotism, that the photo is referring to light. The fact that it's light is actually derived from Helios or the sun is, uh, the very first baby step that you can say is taken to explain the phases of the moon. Now, something follows immediately from this. Once you accept that the light of the moon is intrinsic to it, you can immediately make some conclusions about what the shape of the moon should be, right? So if you look at the moon in the night sky, it's circular, but is it circular like a disk or is it circular like a sphere? If you ask that question, well, if it's circular like a flat disk, there is no reason why you would ever see a crescent moon or a half moon, right? So if the light from the sun is falling on it, then why would only half of the moon be illuminated? That doesn't make sense, right? So again, if you think about these two hypotheses, that it's circular as a flat disk or it's circular like a sphere, um, or it's round like a sphere, the spherical moon hypothesis is the one that explains why you would see a crescent shape. You're seeing a crescent shape because most of the light uh, that's falling on it is actually falling uh, behind it, and so you can't see it from the angle that you're observing from. You can see only maybe part of the illuminated surface of the moon, and not the entire hemisphere that's uh, that's illuminated. So if the moon is spherical, then it must always be half lit, right? Whether or not we see it as half lit from our position or our vantage point, that doesn't matter. It must always be half lit as it's moving through space. Uh, it's just that it changes its relative orientation with respect to us, and which is why we see it going through the phases. But otherwise, it must always be half lit. So that's the shape of the moon, convincingly argued to be spherical and not like a flat circular disk. So now we have two conclusions. One is the moon's light is borrowed from the sun and that it's spherical in shape. Okay, so two steps have been taken. The next step is um, between the sun and the moon, which of them is closer to us, right? Which of them is closer to us? Um, well, um, think about or reflect on the fact that whenever we have a crescent moon, it's not just facing the sun, it's found relatively close to the sun. So we see the crescent moon and the sun, especially when it's a thin crescent, together in the night sky. Here, this picture is taken just after sunset. Otherwise, this crescent might not be very clear. So, so think of the sun and the crescent moon together, right, in almost the same place uh, in the sky. Uh, we have two hypotheses. The sun is closer to us than the moon. Second hypothesis is the moon is closer to us than the sun. Which of these two hypotheses can explain the fact that when the sun and moon are seen together in the sky or close together, the moon is always crescent shaped? It's never fully illuminated. I'll give you 30 seconds to think about this. Somebody asked what horizon means. Horizon is just this imaginary line that separates the land from the sky. If you go look as far as you can, the horizon is just a line that separates the sky from the earth. So if we think about this situation, if the sun was closer to us than the moon, that means if it was in front of the moon, right, closer to us, its light would be falling on the moon from the front side. And if its light was falling on the moon from the front side, then shouldn't most of the moon's surface be illuminated? Shouldn't we see a full moon in that case? But if it is located behind the moon, right, much farther away from us than the moon, then most of its light would be falling behind, would be falling on the moon from behind. And so we see only a thin sliver of light according to that other hypothesis. So once again, these common observations help us uh, identify which of these two hypotheses makes more sense. The hypothesis that the sun is closer to us than the moon actually doesn't make sense, because if that is the case, then whenever we see them together in the sky, the moon should be a full moon. But we always see a crescent moon in that case. So for that reason, we can conclude that um, um, that the light from the sun is coming on the moon from behind, and so the sun must be further away from us. So why do we see a full moon? Well, we must be seeing a full moon whenever the sun is behind us, right? We are sort of looking at the moon from approximately the same direction as the sun. And that makes sense because whenever you see a full moon, you see that the sun is actually on the other side of the earth. So when the full moon sets, the sun is rising, um, and so it's kind of in the same, you know, uh, we are looking at the moon from roughly the same direction as the sun. So uh, given these three conclusions, the moon's light is reflected from from the sun, it's spherical, and it's closer to us than the sun, which means if we were to give it its spherical shell, its own spherical shell, that spherical shell should be inside the spherical shell occupied by the sun, right? So so the moon is nearer because that is the only way we can explain these observations, that when you have the sun and the moon relatively close together in the sky, it's the back half seems to be illuminated. And so if you accept this model, here's another prediction. Maybe it is possible for the moon to come in front of the sun and block the light of the sun, right? That's possible only if the moon is closer to us than the sun. It might block the light of the sun. Uh, if that is what a solar eclipse is, maybe that is what is causing a solar eclipse, then one thing we can say for sure is that a solar eclipse must always happen on a new moon day, right? On a day where we actually don't see the moon at all, right? Because the entire light falling on the moon must be uh, in the half that is not visible to us. And so we don't see the moon at all until it starts blocking the sunlight. And so Anaxagoras, who ironically believed that the earth is flat, and argued that the earth is flat, affirmed that the moon is eclipsed. Let's think about the solar eclipse first. The sun is eclipsed when at the beginning of the month, that means on a new moon day, the moon is interposed, or it comes in between the sun and the earth. Okay, so that's one prediction. The other prediction is that if the light of the moon is actually coming from the sun, then maybe on some days when the moon is on one side in the sky and the sun is on the opposite side in the sky, maybe the earth itself could come in between them and thereby block the light of the sun from hitting the moon, right? And that would be a solar eclipse, a lunar eclipse, right? So Anaxagoras affirmed that the moon is eclipsed when the earth comes in between the sun and the moon. And again, if this is the mechanism behind why lunar eclipses happen, lunar eclipses must always happen on a full moon day or night, right? Um, because for the earth to come in between the sun and the moon, when we look at the moon, we must be looking at it from the same direction as the sun, right? So we should be seeing a full moon whenever a lunar eclipse happens. And that is indeed the case. Lunar eclipses always happen when the moon is full. Solar eclipses always happen when we have a new moon. And so this hypothesis behind or this explanation of eclipses actually fits all predictions. And that's why it's found in our science textbooks still today. But the origin of this goes back even before Aristotle, and ironically to a philosopher who actually believed the earth is flat. And we'll come to him shortly, because I want to go back to what Aristotle wants to argue now. So Aristotle is saying that if you accept this explanation for lunar eclipses that I just went through, uh, that lunar eclipses are caused when the Earth comes in between the sun and the moon, then what you are seeing when you see a lunar eclipse, this dark region that you see when you see a lunar eclipse, is really the shadow of the Earth. It's really the shadow of the Earth that's falling on the moon. Now, this shadow, or the shape of this shadow, for Aristotle, is something that gives us clues about the shape of the Earth, because uh, there is no other event that we can observe where the shape of the entire Earth can be seen in any, it's not possible to see it in any other way. But during a lunar eclipse, uh, we might be able to see it, and the outline seems to be always curved, which is what Aristotle points to. So if we go to his words, how else? So if the Earth's not spherical, then how else would eclipses of the moon show the segments that are shaped as we see them? Um, the moon goes through different phases. Half moon, gibbous means it's illuminated more than half. Concave means it's like a crescent shape. So it goes through different phases, but during eclipses, lunar eclipses, the outline is always curved, right? When you have a half moon, the outline is straight. Um, when I say half moon, I mean really a quarter of the moon visible. But um, in eclipses, the outline is always curved. And since it is the Earth coming in between that causes the eclipse, the shape of that outline is going to be caused by the shape of the Earth's surface, which therefore must be spherical, according to him. So this is his argument for, and his second argument for how do we know that the Earth is spherical. Now, I told you that Anaxagoras, who came up with the explanation of eclipses, believed the Earth to be flat and in fact supported by air. Um, so, how could a flat Earth, how is it that a person who uh, believes that the Earth is flat could come up with the correct explanation for eclipses? Well, it's not easy to um, blame him, because uh, actually, if you have an Earth that is uh, flat but circular, nevertheless, it can also, this kind of a circular disc-shaped Earth can also produce a shadow on the moon that is curved, right? So uh, just because the shadow of the Earth on the moon is curved does not prove in itself that the Earth must be spherical, because as you see from this angle, um, you can get the shadow of a circular disk on the moon, which will naturally be curved. But here's what Aristotle is pointing to. Lunar eclipses happen um at different times, like different lunar eclipses happen at different times, right? So if you if you think about lunar eclipses that happen when the moon is further lower in the sky, if the Earth is flat, then when it blocks the light of the sun, and think of making this even more extreme, when the sun is, just about, below the horizon here, and the moon is just above the horizon, the shadow of the Earth on the moon is going to be a very thin band, right? It should not be, it won't be like this. It won't be like this, right? It would be in the shape of a thin band. And so some lunar eclipses might have shapes like this, but other lunar eclipses, if the Earth is flat, would produce a different shape on the surface of the moon. And Aristotle's point is that every single lunar eclipse produces the same um, outline on the surface of the moon, which means the shape of the Earth from all angles must be circular, and so it must be spherical. All right, so that's his second argument for why the uh, how we know that the Earth is spherical. Any questions about this? So actually, if you think of cosmologies where the moon is farther than the sun, like in ancient Indian um, uh, cosmology, the moon was actually farther than the sun. And one possible argument for that, which is also reasonable, is that, the sun, we feel the heat from the sun, right, when we are out in the sun. Whereas if you go out when the moon is, there in the night, again, the assumption is that the light is intrinsic to the moon. We don't feel heat from the moon. In fact feel like it's cooler at night, right? So, um, so it's reasonable to think that it's further away from the sun. But here's the problem: if you put the moon further away from the sun, it's impossible for it to then block the sun from the front side. And so one must postulate some other invisible entity uh, that is blocking the sun, which we don't see except during a solar eclipse. So I think somebody asked, like, why did they always think of supernatural things? Well, sure, I mean, there are details that are supernatural there, but also think of it this way, that um, for whatever reason, if you put the moon further away from the Earth and the sun, there cannot be anything that blocks the sun from the front, right? So if you want to bring something, it must be invisible for the rest of the time. And so that's why, you have this new planet uh, in um, ancient Indian cosmology called Rahu, which is perceived only during a solar eclipse. And the same thing for a lunar eclipse, actually. So the sun and the moon are actually, kind of always above the flat Earth, right? I mean, if you think of the Earth as extending all the way to the edge of the universe, you can't have the sun and the moon. Uh, you can't have the sun uh, on the other side of the Earth or below the flat Earth, right? That doesn't make sense. So uh, it wouldn't block, like the Earth wouldn't come in between the sun and the moon, because the 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 order is that you have the Earth, then you have the sun above it, and then you have the moon that's going above it, right? In orbits that are also kind of flat, right, above the plane of the flat Earth. So in some cultures, when the sun sets, it's just going far away. It's not like it's going under the Earth, it's just going far away. It's staying above the plane of the Earth, but it goes so far away that its light stops coming to us. And at least in my reading of the Puranas and all that, that seems to be the cosmology there. And so the sun is always above the plane of the Earth. The moon is always above the plane of the Earth, and the moon is actually farther than the sun. So it's impossible um, for the Earth to come in between the sun and the moon. So then you need another planet uh, to to explain a lunar eclipse, right? What could be coming in between moon and the Earth to cause a lunar eclipse. So you have Ketu, or sometimes you have the same demon Rahu uh, uh, causing both eclipses.
So in a way, we could say that, like, just because we did not have a scientific explanation about all of these things at that time, we came up with a, a hypothetical explanation, which now we can, like, in today's date, we can disapprove of, because now we know the facts. But at that time, we did not. So it was just an explanation to fill in the gaps.
Yeah, yeah. And from that, you see, if you think about it from the perspective of that time, you can call it scientific, right? There were a number of scientifically argued viewpoints about things that were subsequently replaced with better explanations. So we might call them unscientific today, but most of what we believe today might be unscientific too if travel 500 years in the future. So um, uh, um, so I don't want to like necessarily use the word like for example Aristotle's physics, is it unscientific? Well, yeah, we don't accept his physics today, but it was considered to be very scientific for 2000 years. It's not because people were dumb, but because it explained so many things that no alternative viewpoint could explain. And so that's the nature of science. So there
Yes,
were a
sir,
lot of
that is true.
developments. Yeah, you can have a pretty elaborate flat Earth cosmology, right, which explains as many things as possible. And the attempt there is to explain things logically, but you can have that viewpoint replaced with a simpler viewpoint which explains many more things in the future. So uh, um, that doesn't mean the older viewpoints were unscientific in a derogatory way. They could, after all, knowledge is cumulative, right? So you always build on top of what was already there. And if you are completely starting from a blank slate, then it's not possible to develop Newtonian mechanics from a blank slate. You have to, you know, start from Aristotle's physics and cosmology and then make your way to it.
Yes, sir.
So there's another argument he gave, a third argument. So actually, what we've seen is the first argument is not something we accept today. For him, it was the main argument. The second argument was kind of like secondary argument for him, but actually it is a valid argument even from today's perspective. Um, a third argument he gave was by noting again in the night sky what kind of stars are visible in northern regions and southern regions, right? I've told you how north and south were defined in the last session. The direction of the pole star gives you the direction of true north. And so if you look at stars that are in the northern sky, right, in the northern side, and stars that are in the southern sky, what you will find is that stars that are visible from, say, Egypt, when you're looking south, if you travel to Egypt, like the Greeks could travel to Egypt, and if you look south, you're going to see some stars in the southern sky, which you cannot see if from Greece, right? So from more northerly lands like Greece, you cannot see some of the stars that are visible from Egypt. And likewise in the northern sky, uh, uh, maybe from Greece, you see some stars to be circumpolar, right? Which means they always lie above the horizon. They never set, they never rise or set. They always stay above the horizon going around the pole star. But from Egypt, they might appear to be setting and rising. So, according to Aristotle, this observation from two different places on the earth, Egypt and Greece, also points to the uh, earth being spherical, because let's think about it from two different perspectives. One is a flat earth, right? If the earth was flat, then a star that's above the horizon for someone in Greece should also be above the horizon for someone in Egypt, right? Yeah, maybe the elevation could be a little different, but a star that is visible from Egypt must also be visible from Greece and vice versa. So it doesn't, this kind of observation contradicts um, um, a flat Earth. But using a spherical Earth model, you can uh, explain it. And I'll just give you a simple example, and then I'll see if I can open a piece of software and a planetarium software to show the same thing. So let's say this is a spherical Earth, and let's say there is a star like the pole star that is directly over uh, the northernmost region, which on a spherical Earth would be, if you keep going north, right, you're going to eventually reach the North Pole. So let's say there is a star that's directly over the North Pole. Now, if you go south from there, so here you can see it above your head. If you go south from there to, let's say, the equator, so you are on the equator now. So when you look around you, the horizon line would be like a tangent line, right? So I have shown this star to be really close to the Earth. Obviously, it's not close to the Earth. Now imagine pushing this far out till almost infinity, right? So if you are on the equator, right, or you're standing on your, well, you're standing on your feet, but your feet are actually pointing there now. You would see this same star, imagine it's infinitely far, you would see it close to the horizon, right, or at the horizon. Now, if you go further south, let's say you go to this point, now the horizon for you is like that, and it is not possible for you to see this star, right, because the Earth itself is blocking your view of that star. So this simple example can show you how from different points of the Earth you would see a different set of stars, because the view of other stars would be blocked. So if there is a star, let's say, that's visible for someone on the near the South Pole, that star will never be visible to someone who lives near the North Pole, because the Earth is blocking their view. Right? So that's the kind of observation which Aristotle is pointing to, although he is pointing specifically to Egypt versus Greece. I gave more extreme examples here. Um, but that's essentially his third argument, that which stars are seen from northern and southern places would be totally different. So also think about the fact that for this person, this star is always circumpolar, or actually, even if you think of this person will see that star as uh, always visible, right? Always above the horizon. But for someone here, um, or for someone, let's say, near the equator, that star might be um, um, rising and setting, may not be circumpolar. And so that is also explained um, using a spherical Earth shape. It cannot be explained with a flat Earth shape, because something that's above the horizon should be above the horizon for everyone. So there is this
So
piece
at
of
this time,
Mhm.
so at this time, had they already discovered the fixed stars in the sky?
Fixed stars in the sky. Well,
Yeah,
the
like there's a
poles.
pole.
Yeah, so actually it's a little more complicated, because the pole star itself was not exactly at that center when you go back several thousand years. So there is something called precession that happens where the center around which all the stars are revolving, that that center itself moves, right? Which star is at that center appears to drift and change in a way that every 26,000 years you come back to essentially the same star, like the pole star. So pole star is right now close to the center. It has been there for a couple of thousand years. But if you look at, if you come back, say 7 or 8,000 years later, which obviously you can't, but if you look at planetarium softwares like the one I've opened here, you can actually go to any date and any time on that date and any place on the Earth, and see what the night sky would look like on that particular date. So this is a software called Stellarium, and what I'm going to do is uh, actually, let's see, which place am I in? Are you able to see my screen?
Yes, sir.
So you're able to see the grass and the sky here, right? So
Yeah.
yeah, I'm just going to change the location. Oops, location. Let me change it to, say, a place in South India. Okay, so I changed it to a place in South India, and what I want to do is what I want to do is uh, remove the atmosphere. Okay, so this software allows me to remove the atmosphere, which means even in the daytime, I would see the stars. So right now the problem is that you don't see the full picture of where the stars are, because when the sun rises, you can't see them. But if you remove the atmosphere, you'll be able to see them all the time. And that way you can track what's happening across literally 24 hours. So I don't know if you see here, there is at the center of the screen on the horizon, there is this word N written, indicating that I'm looking north. Okay, and I can actually speed up time here. I can speed up time here by, let's see, yeah, let me speed it up like this. So a full circle is made every 24 hours. And let me also see if I can start the constellations. Oh, the constellations are already there. Okay. So you can see all the stars going around Polaris here from South India. Now I'm just going to rotate my vision and look uh, south. Why am I not seeing an S? Oops. Okay, now I'm looking south. Okay. Now looking south, I see a bunch of stars rising and setting. And I don't know if you see this bright star called Canopus that is just setting now. If you wait for some time, it will rise again from here. Um, there it is. It just rose. It went high up in the sky, and now it's coming down, 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 and now it has set. Okay, this is visible to those of you uh, who live in South India, and possibly even those who live in North India, because if it's visible from Egypt, it should be visible from most places in India. Now I'm just going to change the location to Greece. So I go to the settings and I change my location to, let's say, uh, yeah, somewhere around Greece. And now when I look at the southern sky, I cannot see Canopus rising or setting. I just cannot see it. If I go a little further south, I might be able to see it. Let's say I go to the Mediterranean. Okay, maybe the northern coast of Egypt. Now you see Canopus is rising. But it's not rising very high compared to what we saw from South India. It's rising a little bit, uh, and then setting. So here it is. It just came up and now it came down. So this is the observation that Aristotle was referring to. And actually, if you look north here, you see that Polaris is further up in the sky, right? Compared to South India. So you're going to see a bigger radius for those concentric trajectories of the stars, right? That means more and more of the stars, the entire constellation. um okay, let me talk about stars. More of the stars will have their trajectories visible entirely above the horizon, right? They never rise or set. Whereas, let me show you what happens when you go to the equator. If you If I again change the setting to, let's say I go to somewhere close to the equator, now you see that Polaris is really low in the sky, right? So almost no star is going to have its trajectory always stay above the horizon, right? Very few stars will be circumpolar. Polaris itself will be at the horizon. If I literally went on the equator, I'm still not exactly at the equator. If I go south of the equator, I will not be able to see Polaris at all. So this happens only because the Earth is spherical, right? You cannot explain this using a flat Earth hypothesis. And so it makes sense, therefore, that uh, that the Earth must be spherical. So this third argument of Aristotle, hopefully you understand this now, is also valid today. It's not incorrect. It's valid even today. Any questions about this third argument?
Sir, I have a question.
Mhm.
So, like, there are certain stars that are visible from certain places on the Earth.
Hmm.
Sir, I'm not sure. Could you please answer this one first? Because the doubt that I have is related to this question. Are the aurora lights related to the stars and the movement of stars?
Are we what? Sorry?
The aurora lights
Hmm.
in the North Pole and South Pole, are they related to the movement of stars?
No, no, they are not related to the movement of stars. They have to do with the Earth's magnetic field uh, encountering the solar wind and uh, 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 basically causing it to deflect and then you know uh, um, that's a topic that would probably be explained better once you study optics and modern physics. It's not something that can be explained using the astronomy that we are learning, right? So the
Okay, so
different,
the doubt,
yeah, so the
right? Okay,
colors
so
and
the
all
doubt that I
that would
have,
be from the electrons, excited electrons rather than you know uh, anything to do with the stars.
got it. So my doubt doesn't make sense right now. I'm sorry, my mind is just like in complete places. Yes, sir.
Yeah, yeah, sure. So all right, so that's the third argument. Now the fourth argument is actually quite interesting. He refers to the distribution of elephants. And here's the argument. For the Greeks, this was the world map. This is actually uh, one of the earliest world maps from the time of a philosopher, mathematician whose name was Eratosthenes. And you can see here that India is the is at the eastern edge of the Earth's landmass, right? So I don't know if you see here, but there is this Ganges, the Ganga River, that's actually flowing into the Eastern Ocean here. All right, so you don't see any China here actually. You just see India. So and at the left extreme you have Africa, right? And Africa is also very tiny. It's just basically what the region of Libya and Egypt were. That's pretty much what they thought of as Africa. They didn't know about the vast extent of the African continent further to the south. But anyway, whatever, uh, you, as I mentioned, it's cumulative knowledge, so can't really, make fun of them because, uh, that's basically how much they could explore in their time. So, people from every culture would have a very narrow view of uh, the geography of the earth based on their local uh, vantage point. So what Aristotle knew was that there are elephants in Africa, okay, which there are even today, and he also knew that there are elephants in India because Aristotle was the tutor of Alexander, when Alexander was a young boy, and Alexander would send specimens from his conquests back to Aristotle, specimens of animals and plants and all, because Aristotle was really interested in biology above anything else. So Aristotle had, because Alexander came all the way to, northwest India and Pakistan, uh, he was aware about the existence of elephants, right? Indian elephants. So you have elephants at the easternmost extreme, you have elephants here in Africa, but you don't have any elephants in the middle. All right. So why is the distribution of elephants like this? Why are elephants only found in the western extreme and the eastern extreme of the spherical Earth? Well, according to Aristotle, it must be because these two places at the extremes are actually quite close together on the other side of the Earth. And so maybe there is a passage for elephants to, or there was a passage for elephants to actually travel from Africa to India from the other side. So here are his words. Those who imagine that the region around the pillars of Hercules, actually he's referring here uh, to the rocks that are found on the either side here. Here you have the Rock of Gibraltar. It's a very narrow passage where the Mediterranean Sea meets the Atlantic Ocean. So this is the exit point, right, for those who are exiting the Mediterranean Sea to go into the Atlantic. So he says that those who imagine that the region around that point joins to the region of India on the other side of the earth, and in this way the ocean is one, are not, it would seem, suggesting anything incredible. So he's a little hesitant to accept it, but he's saying that's not really a silly argument. They produce in support of their argument the fact that elephants are a species found at the extremities of both lands, and this is because of communication, right? A physical passage maybe between those two extreme lands. So this is something which we know is an incorrect argument today. Actually, there were elephants even in the middle, but that was during the ice ages. We call them as mammoths, and they were hunted to extinction by ancient humans. But this argument by Aristotle is not an argument that we would consider a valid argument today. So his first argument based on his physics, and the last argument based on the biogeographical distribution of elephants are both questionable arguments from today's standpoint, but the middle two arguments are still valid. And
Tumkar,
so
tell
these
me
are,
this thing.
Even if
Just a
yeah,
quick thing, Tumkar. Did Columbus follow Aristotle's model, or the advanced model had already come? Because Columbus was trying to come to India, ended up in America, right?
yeah, he was actually following, you can say, roughly Aristotle's cosmology, but uh, that model was refined, and actually, once you accept the Earth is spherical, then you can ask, what is its size? What is its radius or diameter? So that had been calculated after
Okay.
Aristotle by, um, actually, even Aristotle, in Aristotle's time, he was aware of some of those calculations, but Ptolemy was actually a very influential astronomer, um, who also gives some figures for the size of the Earth. And so Columbus was following some of these calculations that were done by different people later. And I'll mention briefly about Columbus also in a few minutes. So Ptolemy was
I,
actually an astronomer. There are many
sorry.
Ptolemies in history, but the Ptolemy that we are talking about lived, uh, you can say, almost 200 to 250 years after Aristotle died. When Alexander died, Aristotle also kind of died a year later.
So
Uh,
there's a question.
yeah,
When Aristotle got the specimens of the elephants, did he
no,
not
not elephants,
notice,
not specimens
sorry,
of
the
elephants,
animals?
but smaller creatures. Yeah,
Yeah, the animals, like the specimens.
yeah.
So did he not notice the differences between the elephants of, India and essentially Africa at that time? Like there must be
Uh,
differences, but if there are
we
differences, how can? Like it doesn't make
Yeah.
sense.
Well, there are differences, but you don't find elephants anywhere else. So the differences can be, uh, I mean, uh, now you know, right, that there are um, species of birds or animals that have been recently separated, and so they have not had enough time to evolve. So they still look similar to each other, but at the same time, we also have species that um, uh, are different, but they still don't look that different from each other just because the environment they live in has been stable. So just by looking at physical similarities or dissimilarities, you may not be able to conclude that, that they are different. I mean, compare the main pattern is that there are no elephants anywhere else except for those two extreme regions. And so the fact that they are elephants matters more than, you know, the fact that there are differences between, the morphology of Indian elephants and African elephants.
Oh,
Does,
okay.
does that
Yes,
make
sir.
sense? I mean, we are not, yeah. So, um, so Aristotle gave these four arguments, and there were a couple of new arguments that were added on to these arguments later. And I'm just going to mention a couple of those arguments by Ptolemy. I'll come back to Ptolemy maybe next time because Ptolemy's model of the cosmos was an extension of Aristotle's model, and it was the best model that made the most accurate predictions. In fact, um, I think this model is still used in planetariums to show the night sky because it's a model that's based on the Earth's vantage point because he believed he accepted Aristotle's physics, and so the Earth was stationary at the center. And so the description of the night sky and the positions of the planets and all were calculated in extreme detail by him, and it was the most accurate model we had uh, for almost 1500 years. But anyway, Ptolemy is said to have made this quote that I know my day's life is marked for death, but when I search into the close revolving spirals of stars, my feet no longer touch the earth. Then, by the side of Zeus himself, I take my share of immortality. So, astronomy for him was a deeply spiritual experience. He was a Greek, but he was living in Alexandria, a city in Egypt that was built from scratch by one of Alexander's generals. And it became the intellectual center of the Western intellectual tradition for, after. Um, Athens sort of declined. So this was the go-to place in the Western world for all scholars, whoever wanted to do any kind of research. The Library of Alexandria had um, supposedly more than 500,000 books, and the best scholars were invited to come and live there. They were paid to come and live there, no taxes. They just had to do their research and teach others, much like a modern university. So that's where Ptolemy lived, and he did his astronomy from there. And he's not to be confused with the pharaohs who were also called Ptolemies, the Greek pharaohs who ruled Egypt after Alexander. There were a bunch of Ptolemies there. So we're not talking about those. This was the astronomer. Now, one of the arguments he gives is called the delay of dawn, and it's something like this is also found in Aryabhata's work. Uh, so the argument is that um, if the Earth is flat, right? If the Earth is flat, then when the sun rises above the horizon, it should rise at the same time for everyone on Earth, right? So everyone should see sunrise happening at the same time and sunset happening at the same time. But if the Earth is spherical, then sunrise will happen at different times for different people on Earth, and that's basically the argument that it's possible to see that the sun and the moon and other stars don't rise and set at the same time for everyone on Earth, but always earlier for those living towards the east and later for those living towards the west. So this is, of course, a correct argument. You can call your friend, or right now you can see, for that matter, or I can open my windows and show that it's nighttime, and I know that it's daytime for you there. But if we were closer, in relatively closer, maybe a few hours apart, then you could open your window and show me that sunrise has happened when it's still dark for me. So, or you can just make a phone call nowadays. But the real challenge is how could someone in the ancient world that time, when they didn't have any uh, telephones or watches for that matter, how could they know that sunrise happens earlier for those living in the east? Because they didn't really have very accurate clocks either, and the clocks that were made of sand, it would be very hard to travel with them, because every now and then you would have to replace the sand, or if it's some kind of instrument where you have water dripping down at a steady rate, even that, like when you're carrying it, that itself would disrupt its flow. So, like, it's very unclear to me that this is really a separate argument, or this is more like a prediction. This is something that follows if the Earth is spherical. But using this as evidence to conclude that Earth is spherical, I'm not sure if anybody did that. This seems more like an argument that sort of add on after you already know that the Earth is spherical. Or another option is that this argument is inferred from the next one. So the next argument is actually an original argument, which uh, which is about the time when a lunar eclipse happens. So going back to this explanation for lunar eclipses, here's a simple diagram. So you have an Earth that is spherical, and let's say you have the sun here, and the sun, sort of rises from here, from the east, and it goes around and sets in the west, and so on. So at this point, there is a lunar eclipse happening. So the sun is somewhere here, and the moon is on the opposite side. And so it's a full moon seen by both, I mean, seen from three different points on the Earth. The moon is a full moon, and then a lunar eclipse happens as the Earth enters uh, uh, y- this region and blocks the sunlight and casting a shadow on the moon. Now, um, for an observer living at location C on the Earth, the sun is just about to rise, because, as I said, the sun is going to go like this. And so, if you think of the horizon plane at sea or somewhere close to here, the horizon plane, the sun is just up below the horizon, and it's going to rise soon. So, this lunar eclipse is happening a little before sunrise. But if you look at, if the same eclipse that is observed by this person B at a different location on the Earth, for that person, the moon is actually quite high up in the sky. So this eclipse is happening in the middle of the night. And for this person A, uh, the sun has just set, because the sun went like this, right? So the sun has gone below the horizon, and uh, so if you think of this drawing a tangent line at, or tangent plane at A, that's the horizon plane. So the moon would have just risen, the sun has just set, and then this person sees the lunar eclipse happening relatively early in the night. So if you if you gathered accounts of lunar eclipses from people or astronomers who saw them from different places on Earth, especially in the east-west direction, right? Somebody in Persia, somebody in Greece, and maybe somebody in Italy, you would find that they would have seen the lunar eclipse at different times in the night, right? Somebody saw it just before sunrise, somebody else saw it in the middle of the night, somebody else recorded it just after sunset. And so, what Ptolemy says is that eclipses, so the lunar eclipse is an objective event, right? When the Earth casts a shadow on the moon, it's not like different people on Earth will disagree about what's happening. Everyone will see the shadow on the moon at the same time. It's an objective event. Um, so they are not recorded at the same hours for everyone, these lunar eclipses. We always find later hours recorded for observers that live more on the east than those who are living in the west. And since the differences in the hours is found to be proportional to to the distance between the places, so the further east-west, the larger the east-west distance between those two observers, the greater will be the time difference uh, recorded by them for when the eclipse happened in the night. And so According to Ptolemy, it's reasonable, therefore, to suppose that the surface of the Earth is spherical. And this is also actually a correct argument. And so the delay of dawn argument might just be related to this. It just follows from this, because if you accept this argument, a lunar eclipse is happening uh, at different times for different people, and note that the sun is exactly in the opposite direction from the moon that time. That means the sunrise, it follows that the sunrise will also happen at different times for different people. So I don't really look at this argument as a separate argument from this. It's something that directly follows from this. This is an event that is objective, and so it's possible to record it. You don't need the same person to travel east to west and recording, at what time a lunar eclipse happened. You can gather that information from people who are living uh, in different places. It's an objective event. It happens. It lasts only for an hour or so, and so uh, it's something you can rely on. The final argument is an argument that was referred to by someone um, earlier, and what Ptolemy points to is when you look at uh, what you see when you're sailing in the ocean, when you're sailing towards land and you see mountains. Um, what you find is that the mountains appear to rise up from the sea. Um, so they appear to have been submerged before, and then they appear to have risen up. And let me show this through a picture here. So imagine that you are living on a flat earth, okay, and you're sailing in a ship, and you're sailing towards this piece of land here, this mountain here. So what you will see when you are farther away is that this entire mountain is visible, but it appears to be really tiny from far away. And as you get closer to it, it appears to become more magnified. It appears bigger. But the entire mountain is visible at all times, right? It's just that it appeared to be smaller, and then it appears to be bigger when you get close. But if the Earth is spherical, then when you are far away and as you're approaching this mountain, you're going to first see, as you can see from this line of sight, you're going to first see the top of the mountain before you see the bottom, right? I hope that's clear. You're farther away, you see the top of the mountain, and at this point, you can't see the bottom. Once you get closer, then you can see the entire mountain, right? So that, um, um, so in reality, what Ptolemy says is this is what we see happening. We first see the top, and then we see the bottom. And maybe, you can have, uh, you can test this by having people, somebody light a fire on top, somebody light a fire at the bottom, and uh, maybe of different colors. And so you would see this color before you see both the colors, right? So that can be tested. And there's a complementary observation you can make when you see a ship sailing away from the shore. Uh, then on a flat Earth, you see the entire ship um, becoming smaller as it goes away. But on a spherical Earth, when you see a ship sailing away from the shore, you will see the hull of the ship, the bottom part of the ship, disappear before the mast or the top of the ship, that vertical pole, the top of that vertical pole. So at this point of time, this observer can still see the top of the mast, but the bottom, the hull, is not visible anymore, right? So, uh, whereas if the Earth was flat, then you should continue seeing both the top of the mast and the hull of the ship. Uh, it's just that as the ship goes away further and further, both become hard to see. It's not like one of them disappears, the hull disappears before the mast. But on a spherical Earth, you would expect the hull to disappear before the mast. And since this is what observations show, and not just show in one direction, in all directions. If you saw this happening only in one direction, maybe you could say, well, maybe the Earth is locally a little curved, you know, like mountains and valleys, a local ripple that might be blocking the view of the ship. But when you see this happening every single time in all directions, that means the curvature of the Earth must be like that in every single direction, which supports the idea that it is spherical. So whether you look at it in the north-south direction or east-west direction, it doesn't matter. The Earth must be curved like that in every direction. So it's spherical. Okay. So uh, this is why, on the top of the mast of the ship, you have a platform, an observation platform called the crow's nest, where there would typically be a person standing or sitting, keeping an eye out for land or enemy ships or whatever, because this person would see uh, land or other enemy ships before anybody on the deck of the ship sees them, right? Because just imagine this arrow going in the opposite direction here. The line of sight of this person would extend all the way to till here, whereas people sitting on the hull, they can't see this man standing on land here. All right. So, uh, last couple of minutes here, we've seen that the conviction that the Earth is a sphere goes back all the way to ancient Greece. We saw the earliest recorded arguments for the spherical shape of the Earth given by Aristotle. Now, Aristotle lived almost 2000 years before Christopher Columbus. Columbus, as you know, attempted to reach Asia, specifically India, by sailing west, um, from Spain. He thought it would be easier to reach uh, Asia this way, right, by sailing west, because if he had to travel east, he would have to travel all the way around Africa, right, which would be too long. Whereas by traveling west, he could directly, uh, reach Asia. He didn't know, of course, about the existence of the American landmass, and he grossly underestimated the distance to Asia. And that's where, Kapil, I think, was asking about whether he was aware of the spherical Earth and this. Well, he was aware of the spherical Earth, but more importantly, the size of the Earth, the size of that spherical Earth he was relying on was actually an underestimate. So, not just that, um, the geographers that he was relying on, they overestimated the distance from here, from the western end of the known landmass to the eastern end. So, if you think the Earth is smaller than what it actually is, and if you overestimate this distance, that means the distance that you think uh, you will need to travel on the other side to get to Asia or India would be very small. So, um, so he was a lot more confident, I guess, than what he should have been about getting to India without much of a hassle.
Omkar, I
Um,
think he might have underestimated by around 6,000 miles, right?
yeah, I don't remember the exact figure, uh,
I was
but
just
it was
thinking
quite a bit. It was, yeah,
when I've taken a flight from Delhi via either Heathrow or via Munich, and when I've taken a flight via Singapore, which is Pacific via Atlantic, it seems it would have taken a lot of time for him to reach Americas. First of all, he would have assumed that first landmass while he'll hit would be India, and if he had continued, yeah, it's a gross underestimation, I guess.
yeah. But he knew the Earth was a sphere, and hypothetically speaking, uh, even if he, you know, didn't know that the Earth was sphere, there's this misconception that he proved that the Earth is spherical. Well, by reaching the American landmass, you don't prove that the Earth is spherical because America is not Asia, right? Although it took some time for people to realize that. So, I mean, he and others called the people living in the, Caribbean regions and all where they landed as Indians. But it took some time to realize that this is not Asia. So he would have needed to further journey westward uh, to reach Asia before his journey would count as an empirical proof for the Earth being spherical. Actually, the first such successful journey was undertaken by the expedition of Ferdinand Magellan. And in fact, that expedition was a complete circumnavigation of the world, and it arrived back at the point from where it had started in Spain. But Magellan himself was, I think, killed in the middle of the expedition, but 18 or so of his men made it back. So anyway, we've sort of, I think, come to the end of today's uh, class here. There's this, I'll just leave this link here. It's just a video of, zooming out from a particular park in San Francisco, successively zooming out, and, how within a span of a minute or so, you rise up to see the entire spherical Earth. And yeah, so the arguments that we went through, thanks to Aristotle, were actually the earliest arguments that you can identify as distinctly scientific, right? Some of them were wrong, some of them were right, but notice that they relied on a combination of observations and reasoning, uh, not appealing to authority of any person or any text, but relying on taking responsibility to justify why they thought the Earth was spherical. How do we know that the Earth is spherical? Why is it spherical, and how do we know?
So there is a
So,
question
mm,
that comes to my mind.
mm,
So like you mentioned that the like because the Earth was spherical, so the observation point on the ships was at the top of the sail, so that they could see land masses and enemies and whatnot before, like they had some time to for themselves to actually save themselves. So the question that I have is that right now as well in the present day, when we want to see stuff, we seek a higher point so that we have a bigger vantage point. So
right.
is it somehow related to like now, like it's just common sense, but is it somehow related to the spherical nature of Earth right now as
Yes,
well?
it is.
Not necessarily, because there might be things that you want to see which are blocked by obstacles that might be short enough that if you went to a higher uh, vantage point, you would be able to see over, right? Like maybe you're in a forest and you don't know how big the forest extends. But if you climb on top of a mountain, you can see how big the forest is and what potentially lies on the other side. So uh, it's not exploiting this fact that the Earth is spherical. It's just exploiting the fact that even on a flat Earth, you have an uneven surface, and so your view of things that are far away are blocked because of that uneven surface. So the more you can rise up, the more you can look over those obstacles.
Okay, but like uh, Aristotle's argument still stands today, or not?
Some of them do. Two of them do. Two of them don't, as we saw here. Well,
And if we like, specifically talk about the ship thing, the spherical, the like the height thing,
yeah.
does it
So
still
this,
stand
like
today?
I said, these two arguments are valid. This one is also valid. Uh, this is valid, and this is valid. This is something we would not accept today. This is something we would not accept today. So
Okay, yes,
Aristotle, of course, gave these four. So two of his arguments are considered acceptable even today. The other two, the most important argument from his perspective was this, which we don't accept today because his physics has been replaced with a totally different physics. And so my main purpose
yes.
was actually, uh, even though his physics occupied a relatively small fraction of time in the class, but this, you know, ha being able to understand his physics and how it supports his cosmology is going to be critical when we move. I think maybe if not in the next class, the class after that, when we move forward 1,000, 400, 1,500 years forward in time and start looking at an alternate um, view of things based on new observations from telescopes, which will challenge the old astronomy. But you cannot just challenge the old astronomy without having a new physics in place. Otherwise, your new astronomy is not going to be accepted, as
Obviously.
Galileo found. Yeah.
All right. So this is good. Guys, any more questions? I think, again, as I say, it is beginning to make more sense to me. Omkar, by the way, I sent you on WhatsApp. This guy got Nobel Prize in 97, and he said, it seems Aristotle was our superhuman like Newton and Da Vinci and Galileo in erstwhile years. So it seems Aristotle had an opinion, had a perspective, and a theory about everything. But fantastic, very good. So, guys, we are going to meet on Wednesday. We are going to upload this video on the YouTube channel, hopefully tonight or by tomorrow morning. And we are, I think, going to move into Galilean physics in the next class, which is going to be on Sunday. But on Wednesday, we will meet for another class that is not going to be this journey we are on right now. It is going to be about using some of the maths like we did for radiance last time into
Yeah, actually,
physics.
I can talk a little bit about geometry and connect it to what we did today.
Sure.
So yeah, so that way we are able to quickly get to Galileo's trial in the next class in a week from now, and after that we would be pretty much ready to start overlapping with the 1D kinematics in NCRT.
Perfect. So guys, any question or we take leave? It has been 2.5 hours. Omkar, at Omkar's place. I think Omkar, you are at 12 night now.
Yeah, almost midnight. I mean,
Okay.
I'm okay if there are a few questions. I
And
can
Mr.
take them.
Trump, I got up and I found out Mr. Trump has been shot at, and it was
Yeah.
like, wow, that is quite crazy.